Hello guys, again at joined the Watanabe Bukola for this channel, Nobera Process Designer. This channel is the channel for process design knowledge and techniques. So we upload videos on process simulation, CAD drawing, AutoCAD, PNID, optimization process, any knowledge that is actually related to process design. We upload it and discuss with our viewers. You can always give us feedback and help us by sharing it with your friends and colleagues. Yes, and also commenting any kind of thing that you like to address all this to discuss on our platform. So to cut the story short, so today what we are doing is Aspen Plus simulation of biomass classification process. The journal I'm using is this journal from Dublin Institute of Technology. So actually the I want to cut this short so I can do something before the video run out. So this is like the major processes of they call it the type of process to be FICLB, that is all the full meaning fast internal circulating fluidized process, and it's just having gasification zone, combustion zone, cyclone, and it's just gasification in the process whereby biomass material is burned to produce sales gas. Sales gas in the sense like CO2, hydrogen, methane. You understand that can be used in the industry to produce heat. You understand? So the biomass can be wood chip, can be organic material, can be anything that is just um organic here, understand? Anything that is just organic and you can get the components, you understand, it contain different kind of components that can be gotten from the organic material. So you burn it and you turn it to gas. So that's just like a literal meaning. So this is generally processed. So you have a steam, you understand, you have to pass through steam and the reaction of the biomass, and the steam is given in the where is the reaction? Okay, this is the reaction. So you see the biomass contain a lot of carbon. So carbon will hydrogenate to methane, hydrate to CO, you understand, CO2, methane, and the reaction. So all this reaction is going to be used to do the model, and you have some byproducts here, which is the ammonia, H2S, and HCl. So the process generally is done with Aspen Plus, and this is the flow sheet in Aspen Plus, and this is the components of the, because we have to be using composition analysis like proximate analysis and ultimate analysis to characterize the component, the which is not a standard component. So like carbon chloride, so you have to pay, you understand, you have to model it as a non-conventional component in Aspen Plus, and that's the kind of the power of Aspen Plus ability to model non-ID system. You understand? So we have the ash, the fixed carbon, the volatile metal, the moisture. So after this is the low heating values and the thermal power. So this is the most mass flow rate of the which is the biomass. So this is just like the summary of the process, because the major thing that we are doing is this process like is sensitivity analysis of the, because I've already done the model. So I want to teach you guys how to do sensitivity analysis in your model. Sensitivity analysis is like case study analysis when you vary some of the plant process parameters and check the effects that it have on the output of the plant. You understand? So you know the major range, the range at which that is more optimized. Is it like what you do prior to when you optimize your process? You understand? So you check the effect of the parameters on the operation of the plant, you understand. So that's basically what we want to do. So now the effect of we check the effect of the gasification temperature, that is the temperature that is that is the temperature that the gasification process occur, you understand. And we are going to check the steam to we are going to check the biomass moisture contents, you understand. We are going to vary it and find the effect on the process. biomass ratio, we are going to do that one too. And the air fare ratio, you understand? Air to fare ratio. So these are their results. So we are going to compare their results with what I'm getting, and just to show you that, to show you how it is done. So that's what we're going to do today. So let me move fast to my model. So this is the model here. Yes, I'm following what they have done. Actually, is not yet complete because I'm still working on it before I started this video. So this is the feed come here. So basically, the feed you will decompose into the components. You understand? Yeah. So you like yeast, it's specified as a yeast shift reaction. So you specify the yeast here in the setup. You specify the yeast here. Yes, and for all the components from the biomass and out issue is inert here. So the components attribute of the remaining components. You understand that doesn't react to form these components. You understand? So this is like it's not, you can't find this kind of realistic model in real life. You understand? This is IC or Aspen Plus standard model. You understand? Just to model each reaction. You understand? A simplified reactor, you understand. So this is a separator. So this one separates the, because from this seed you have two type of carbon. One is carbon from the mixed upstream and carbon from the conventionally inert solid. Is a conventionally inert solid carbon that's going to be bond in the combustion zone, because this stoichiometric reactor means we use it to model combustion of the process, that is the combustion zone of the gasifier. You understand? Then this is the gasifier itself. You understand? So then we have non-equilibrium. This one method models the non-equilibrium reaction, that is the reaction of the byproducts. You understand? That is mostly found in the outlet of the gasification process. You understand? So the byproducts can be all these reaction that we have here, all these. Okay, let me first these 4 and 5 reaction. You understand? Then we have the ACl, H2S, and nitrogen BC. So that are the byproducts I can show you. So we have the, you can see flowing is ACl, H2S is from. So you I use a fractional, it also stoichiometric reaction, so I specify fractional conversion to be one. So, but for the combustion process, that one is generated internally. So you use combustion. So using to generate combustion reaction due to the carbon, by burning the carbon. From the okay, when I'll show you the result now. So it's going to just, like I said, clinically, this just set is to separate the the mixed carbon and the conventionally inert solid carbon, yes, and to the one that is going to be sent to the combustion, so, and the one that will be just sent to the process here. So we have the you can see this one is one for the char. So it is the char that is going to be born in the combustion. So this one is going to go to non-equilibrium. So the heat of the non-equilibrium reaction is going to be transferred to the gases, and also the heat of combustion is going to be transferred to the gasifier. Yes. So we have a separator here to separate the non-equilibrium products so that it's not mixing with the gasifier. So we have the H2S and ACl going here. Yes. Then this heater is to cool it down to the temperature of the gasification, because we are going to be changing the gasification temperature. You understand? So this gas is to, when you read the description in this journal, you see the gas is to try to adjust the product of gasification to be more realistic to what we are getting, like to get the composition of snare gas, synthesis gas that is more realistic to what we are seeing in plants. You understand? Just like plants data feeds. You understand? So that's what, so we have nitrogen that will be injected, which also are sort of getting it to be realistic in the sense of there's nitrogen poured in stream in this stream in the gasification process here. So that's why I'm starting nitrogen stream here. So this one would although in the gas, if you have to use a deep free energy, that model zero temperature approach, that means the product is all the product is in equilibrium with each other. You understand? So I specify all the reaction like from this place. or the reaction here. So that's why I specify here. So that's the brief description of the process, and this one is to separate the water out, and you have a dry gas here and the mix with the other byproduct, which is the ACA, the H2S, and the what's the other one? Let me check here. And the ammonia. Okay, so there are few calculator in the process in order to make the system to work well. So you have to use some logical operation in the process. So you have the three different aspect. One is adjusting the temperature of gas, is adjusting the heat, that is the fraction of the, it's just like a way of adjusting the heat of the carbon that is sent to the combustion. So that is the char carbon, and the one that is not combust. You understand? So then we are going to specify, although because from this place the total mass of the carbon that must be, like from the analysis of the proximate analysis of the feed. If you check, this is where you put the proximate analysis, and the, let's say, the ultimate analysis is the carbon contain 51.19% from the ultimate analysis, that is the internal. You understand? So it contains 51.19, so it's yield, the decompose, it's going to yield to carbon. You understand? Because carbon that we need. You understand? So if you check the yield, if you check the total masses, adding these two up will give you 0.55. That is the fraction of the feed. You understand? And the only feed that we are sending is biomass. You check, is biomass. One more mass fraction is biomass. You understand? So just like the logic of getting that. So which one we adjust the the conventional inert solid carbon, which is the char carbon, why we have another calculator that will adjust the second, which is, let me check. Okay, this one we adjust the second yield. Yes, and so that's why I say mixed car. So if you check the two variable, we have mixed car and inert car. This is the second yield. So it's going to be equal to, so the total has to be, the addition has to be 0.511. So you just adjust the second mass fraction as you are changing the inert carbon. You understand? So this one is to adjust the, because in the journal they make the combustion temperature to be greater than, like, 55 degrees Celsius greater than gasification temperature. So this science spec will vary the combustion temperature so that it reaches that temperature, you understand. So it's part of the specification of the gasification process. And we have the nitrogen, which is used to add some nitrogen to the process so that the outlet of the process, you can see it adjusts the, okay, this nitrogen content in the snare gas, you understand. Then it varies the nitrogen gas to the process, you understand, the mass flow, that it's 0 point, the more volumetric, this standard volumetric fraction, you understand, is 0.014. So that's what we want in the amount of nitrogen in the product, is synthetic gas. So going back to the calculator, we have explained the first calculator. So we have the second calculator, which is the, talks about the feed rate and the air to, okay, talks about the air to combustion air ratio, which is we are using 1.1. We actually have a fixed ratio of the air that we are going to be using to combust the jar. You understand? So this one will calculate the combustion air. You understand, from the this ratio that was specified. We are going to be favoring this ratio, like I said, in the sensitivity analysis. You understand? So we have the steam rate, so we have the steam to biomass ratio. So this is the formula for steam to biomass ratio. Is the quantity that was 0.73. So you multiply with the steam rates, then you you add the total water that is sending to the process. You understand? Just total water. Biomass contains some water too. You understand? So this is steam to biomass ratio. Biomass ratio 0.7. We are going to be varying these two. So we have the calculator. This one will set the heater one, this heater on top here, the temperature to be the, like I said, we are using calculator to set it up. Okay, to the gasification temperature. So we have this one which is the calculate the H2O rate from the moisture content. You understand that we specify for the biomass. So easy. So it's going to divide by 100, then calculate the water flow rate. You understand? So you have the large background release, which is setting the temperature of the first gasification to the temperature of second gasification. That is the one I told you we used to adjust the products so that it is realistic, it fits the normal plant data. You understand? So moving from there, I think we can now start with the sensitivity analysis. So I've created two sensitivity, but it's not completed yet. Yeah. So for this sensitivity, we are going to be using from some variables. So I've declared the variable to be steam to boiler ratio, the air to feed ratio. You understand, for this sensitivity analysis. So this differential calculation for it, like I said, steam to boiler ratio is going to be M steam plus biomass moisture content. I call it BMM. Then they fix the M feed here. And but you can define those variables have been defined here. If you check all these variables here, although it cannot be big, but the next one. So we have because we are going to be checking the composition of the product. So we have all the composition here, methane composition of the snare gas, which already this. We have the CO2 composition, H2O composition, nitrogen composition, H2 composition. You can easily add this by just pressing new. You understand that? You show up from here, then it will show up in the reference, so you can pick the same reference. You understand? Maybe standard volume fraction. So look at the H2O composition, you can see. Once I pick, you can see standard volume fraction H2O. So for the biomass, you can see this amount of water in the elements one. Element one is from this stream, because water is from this stream. That's the water is going to be sent from this calculator. That's this calculator I talk. This calculator is going to calculate the H2O rate from the rate, you understand. So it's going to be sending the water here, and the water is not in the comp, so you have to be sending your water here. That's why I put element one. So we have element one, the flow rate of water in this one. So that will give you your biomass moisture content, this which is BMM. So we have the mass of flow here, you understand, and mass flow of steam. So that's that. So so we have the formula for you can see formula to air to fair ratio is going to be MA and MP, because it is you can't really, you have to be varying these parameters, but the way we made the model is supposed, it has to be constant is in the equation of the calculator. So you have to just use another way around to get to vary these parameters. You understand? So because look at this, in this equation it is constant, and it's pretty hard to create a variable here, and to be adjusting the variable with, you understand, to change the topology of the process entirely. So you have to use another tricky way, you understand, to get the result. So and we are going to get the same thing. So so right now I'm going to start. So you have to get the variable to vary. So we can do the simpler one. I think from what we want to do, we want to do the steam to boiler ratio, the air to fuel ratio, and the biomass moisture content, and the gasification temperature. And also from the, like you said, from this model, gasification temperature is calculated, not input variable. So let's do the smallest, the simplest one first, which is the biomass moisture content. So I can add the variable here. So add the um for moisture content, because it's component attributes, you understand, approximate personal, you understand, like proximate analysis of the process. Look at it, part of the proximate analysis of the process here. You see, to moisture, you can see the moisture here, 20%, so 20 which percent, sorry. So we can now vary down and check the result on the process. So we have the component biomass, so we have optional. So element one, just pick the element. So you start with five, then because from this graph, I think it's five they start with. You can see it started with five here and four. So and 40, I mean, so you use 40. I can pick 20 points to where you can calculate way so that it follow it. So you can see this one is custom to do. So now you just pick. These are the this is the place where you put the variable you want to be listed from the variable you define here. This is flowsheet variable. We define the flowsheet variable here by picking, giving it a identifier. You understand? Then you pick the reference to the variable from the flowsheet here. You understand? Then you can define a Fortran variable. You understand? So you can tabulate the two, and the Fortran you write the code for the Fortran variable here like this. I declare to wave 8 like a wave variable. You understand? This steam to boiler ratio and air to fuel ratio, you understand? This is the equation for it. You understand? It's using mass steam dmn divided by mp. This one is mass of air divided by m of it. You understand? So you just have to you have to make sure you are consistent with the units and all this. So this is like command prompt for the control panel for the sensitivity analysis. You understand? So executing, if you wanted to exclude the base case, that is simulation, so you can pick one, some of these formulas, you understand? Or do not exclude the base case, or you can just pick initialize the block. Yes, like there are some blocks that their properties you have to be sending their results. You understand to initialize the blocks. I think you initialize the blocks. You understand? So we have so now I'm just going to pick on the variable where I want to see. So okay, okay, I can just delete this one now. It is not I'm not using it currently. So it's as so now I'm going to go to another sensitivity, second sensitivity analysis. So I'm going to copy the first one, going to copy it and paste it here so that it will be fast. I think it's fast now. So this one to delete the first. So I'm going to do it again when I need it next. So this is the calculation. Here I'm declining like very because we need this to calculate this efficiency. They call it coal gas efficiency. You have the charge with the amount of charge that you split, you understand? The steam to boiler ratio and the air to fuel ratio. So this is the calculation for the gas efficiency. Mass of gas times the low heating value of gas times 100 units divided by MP and BMS. Everything is written in this journal. You can easily understand what I'm doing by reading this process here and follow what I did in this sensitivity analysis. So we have this is the formula for CGSA, you understand, and the low heating value of the gas. So we have the charge speed, the combustion, the charge that is being combusted, and divided by the total number of charge units. So that's the formula. And this thing I've gotten from this defined variable already in this defined variable here. The charge combusted is for char. You can see the stream name char and the components, the substream is conventionally inert solid and carbon. You understand? Kilogram per second. You understand? So the other charge is the one that is sent to gasifier for equilibrium reaction to mix this is the mixed stream, you understand? Carbon kilogram per second, you understand? So that's so this one should be element 3. I think it's better in element 3, it's more realistic. Like no it's element 2. I was thinking it's the element. The name of the stream is somehow confusing. So we have this. Okay, so we can run this and check. I think I have to make this sensitivity analysis active. It's not active. I think everything is working fine. So let's run play and run so that we are getting good results on the onset. So So when I'm done now, when this work, the next thing is to work with the gas station temperature and get the result and compare with what they see, what they get. Okay, result is available, so we can check the results now and compare. So basically, this is their simulation. Um, so we are varying the water content, so we can easily plot this on. It's just the other is just somehow tricky to work with. So contain some ideas. This is the raw version. So this is the result. Go to the result for the biomass moisture. Okay, biomass moisture content. I think they didn't do the first one because if you really they said it has little effect and the composition has little effects on the sorry they said the biomass moisture content has little effect on the composition and we see it clearly now. So by using all the plotting like using the plots, you can see like the lines mostly linear, like straight line and it's constant. I mean constant lines. So that's little effect. So let's check the result of the gas layer tree. So this is the result here. So we can plot like down to on the one result is that is showing me is just I'll tell you the reason why it's showing me the one result now. So it's more like this one to this plot. It's just like the LNG, the scaling for LNG is from 9 to you can get down to 9 to 21. And you can actually the scaling for LHV like low heating value. So this is the just like you can see this one is 14 to 14.8 and what they did is generally around 14 you understand. So it's like constant you understand. So this one is the CGS is inversely proportional like the low heating value is directly proportional. So and you can see it you have the CGS directly proportional. Thank you. Okay, we have this is the CGS here. You understand the inversely proportional. Yes, and the LEV direct proportional. So that's it. So let's do the second one, which is the gasification temperature. But to do the second one, you have to do something because the way the model is being done, we really can't adjust the gasification temperature directly. Yes, and so we have to because the major effect of the gasification, this design spec is like control feedback controller that would try to adjust the temperature of the gasification to be 850 and it's going to vary the mass. So we have to check the range that the mass is being varied. So it's the mass that are going to be varied, you understand, in relation to the gasification temperature, you understand. So right now I'm going to specify the range that they want because in the process the range is this is the range around 650 to 1050. That's the range that they are using in the process. So I'm going to specify it for this place and check my fraction that is giving me from the results because I can easily check the results here. So right now currently the fraction is 0.07439. You understand? So that's the result final value that is able to get this temperature. So I'm not going to specify a lower temperature and get the range. You understand? Then I'm going to store it. Then get the higher one and store it. So that's what I'm going to now use in the scientific analysis. Then I'll now deactivate this design spec. You understand? It's just like using design spec alternatively. You understand? So we have the so this one is going to be 650. So I'm going to specify 650 and run the process to get the temperature that I'm looking for. So it has given me a result. So I'm getting 0.024. Let me write down that 2s 650 is 0.0241349. So check, check. Oh, let me purge the simulation because sometimes it just give you from the was like searching. No. So if you want to be getting some falling value, so you have to put this the result and check from the beginning from the outset. You can see what I'm saying. I think this one is you can trust this value more than the first value. So I'm going to write down this value 0.518942. That's why I say it's better to put the result before you run the simulation again. So I'm going to put it again now. Although it takes some time to run, but you are going to get a result that you trust. And I'm going to give this one 1050. So I'll run it again. Okay, result is out. So let's check the fraction again. So this one is 0.08556. So that's the second one. So now we have the range. So let's change this thing back so that we don't forget. Because sometimes this is a big simulation. When you forget things, you are getting wrong answer. And Aspen Plus form is not flexible. You have to be open forms and open forms all the time. Okay, that's fine. So now we can now deactivate this and do the gassy process. So I will activate my sensitivity analysis again. So now I'm going to change this one to block variable. So become that's the name of the plot. So the variable that I'm using this time spectrum as well is the mass heat. So for components, carbon, uh, the one that is going to jack conventionally in that solid. The way it is substring, you understand? Carbon in the substring. It's a different component, You have three substring, not conventional components, you understand? There is no carbon, there is only biomass and ash that is there. Then we have the conventional linear solid which contain the carbon. Then we have the conventional, you understand, mixed conventional components which contain also carbon that take part in the equilibrium process, equilibrium reaction. We have on this, so I can copy this again, then we have this, so that it will be, okay, let me delete this, paste the one that I copied there, you can see it's basically the same thing. So the next thing is to add a new table for temperature because I'm going to added the temperature, so this one is now going to be 1. So the name is already here to measure the acid temperature, you can see gasified temperature, so I'm going to add it here like this. So that's it. So that's not the name. Because if you are using wrong name, it's not going to work. You have to use the right name. Now you will check active temp. I think that's the right name. Okay. So let me now do this. Okay, this you have to do for the first one too before you run. So you insert. So I'm going to write gasif, the same thing, gasif temp, because the variable is already in the sensitivity analysis. It's already here. You see, I'm still opening it again. So it's already here defined. This is basic variable. So this one too is done. So the next thing is how to run and pick our variable. So this is somehow this kind of thing is because we are having sensitivity system. That's why showing the error. So sensitivity system. Result that we want to put. So right now, let me run it and oh, okay, I've disabled it. Okay, I thought I didn't disable this. So okay, okay, result is out. So I think there's a mistake. There's an error somewhere. Okay, let me check. Oh, we forgot the range. I think I was specifying wrong range. have to copy. That fraction that we did here, we didn't copy it. So this fraction in here that we were getting there, we didn't copy. So I'm going to copy it now. So we have 0.00426204. Then the second one, we do the second fraction. 0.0855768. That's something about working on big. Something you forget little things to showing error. So let me do for the second fraction. We are using the biomass measurement range 0.005, and that's large. So 7204. So we have the second one here 0.0855768. So I hope I didn't make mistake. 0.00526204. So now let's put the result, the fake result, and use the original result. So let's see what happened now. Okay, it has worked. So we have this. So now we can check the plots now. The warning is generally from the flow sheet. Before let's do the warning now because there are some components that are showing warning. All this they come is because of the way the flow sheet is designed, the topology of the flow sheet. Because we are using mass sheet, so mass sheet of the component form, and the component is not in the feed and is in the product. So it's going to do material balance for the component. So when the atomic balance for the component is not equal, so it's just a warning. Although this is generally non like what's known as a non-ID system. So after we are seeing this one, there's no way to remove the warning. And for this one, I think it's because there is one stream that is zero flow. So they didn't do flash. You can see this one is having zero flow, so they didn't do flash calculation. So that's the warning in the simulation. So that's how you are seeing the warning. So let's go back to my results. So let's plug the result and compare with what they got. Okay, results. So we have the so you remove the the is the our independent variable, the x variable. So just pick it here, so you show the plot and the pick the h two. So this is the plot here. So you I want to measure the x axis, y axis together to single plot here. So it's actually more like what they got with yeah, they can see. It's just like the water only is when I compare it, it's like the water flow is starting from 15, but this one is 14. Maybe it's from the configuration or the calculation process. I'm not sure. We have this the water is coming from instead of starting from 30, it's following the same trend generally. You understand? So that's the thing. So the second one is let's plot the second one and check. So the gas temperature, so the gas speed, you can see basically following the same trend as their own. This is the gas speed in black. Although they are using different color from now on, to be changing the color will take time. We are going to do a lot of plots. So we have the gas speed here. So we have the cool gas efficiency, and this is the low eating value in megajoule per kg. So this is the range here. So now so we move to the next level, which is let me deactivate this sensitivity analysis again. So for the air to feed ratio, you activate this. So you test the calculator with let's do the steam to biomass ratio. So I think this is the calculator for it. Oh, no. So I'm going to test it from here. So the range is from let me show you what it did. So the range is from 0.25 to 2. So I'm going to pick 0.25 to 2 and check like what we did for the first one too. So let me put okay. So 0.25. Yeah, the science tech is on. Okay, result is available so we can check, not from the design spec, from the calculator now. Okay, we get to define variable. So you have this one is for the year, calculator 4 is for the, so we have the 75.432. Okay, write that down. That will be the minimum, you understand, for the range. You understand? So we do the second one, the minimum for the range. So the second one is 2. That will be the steam to boiler ratio 2. So you change it to 2 here. And I don't think this one needs to be, because just with the main calculator of work. So you don't need to change in all the over to be faster. If it's not doing all the calculation from the onset. So we have this value 2715.55 kilogram per hour. So that's for the second one. So now we're done. So the next thing is just to change it back to the default value so you don't mess things up. Process, so the default value is 0.75. So I'm going to change it back to default. So that's good. So the next thing is now this sensitivity analysis there. So I'm going to deactivate this because calculator is now the business. We are going to be adjusting the flow directly now. You understand? From the sensitivity analysis. Although even if I leave it, it will not allow the calculator to work because the sensitivity analysis is going to be, we're going to be using the variable, you understand, and it's going to be altering the variable value. So two things cannot control the same thing, you understand. So it's going to drop it all. Not to do work like leaving the control, you have to be making it as simple as possible. You understand? So right now I've just changed the from I changed it to string variable, which is where I'm going to see the steam, the mix, the mass flow. So I'm going to change it now to 75.432 5.55. So that's the range. So you copy this. So this one, let me finish work on this one. So because what they are using is steam to boiler ratio. So and I've already calculated steam to boiler ratio here with these four statements: M steam, then biomass moisture content, then divided by MPP, and that is getting, because all these variables go to be calculated 2 years. So I have to just calculate it so that it is showing the record in the results 2 years. So I'm going to change this one to steam to boiler ratio because we don't really need gasification temperature right now, because I've made the design spec for the gasification temperature to be active again. So the temperature is going to be at 80 K at all time. So we have the steam to boiler ratio here. So so the next thing is just to copy this one again so that maybe something happened. So delete this one so that it should be faster to do. Okay. So change this one. It's over here too. Can see steam to boiler ratio. Okay, tabulate. Wipe it very well. Steam to boiler ratio. I guess that's the name. Okay. So right now everything is set now for the steam to boiler ratio result. So I can run the sensitivity analysis and check my results and my plots and find the relationship between the components and the steam to boiler ratio. Maybe the components both fraction in composition increases or something. Okay, this one is also showing error, but the first one is not showing error. How funny. So let's check. This one is quite fine. Let's check the first one that is not showing error first. So okay, make this one my x axis. Pick the other components. Okay, we have this. Let's merge it together and compare it because they merge it together in their plot. Okay, let's this is what they get. I think like we have to maintain is inversely proportional, like trying to stabilize, you understand, reduce, you understand, like reduce, this is not maintain, no, CO is blue, maintain also reduce, you understand, why the H2 increases and the H2 also increases, H2 composition also increases. So I think let's check with our own color code. We have H2 here, yes, we have H2 increases here. Maintain, yes, maintain box, maintain is box. Met, no, CO2 increases. Yes, maintain. Okay, methane decreases and CO also increases. So I think okay, you can see their CO2 also increases. So like following the same pattern. So let's check it. Let's check the same thing. Okay. This one is showing result. It's showing okay, it's showing earlier. I think is this just to this case study two that is showing the error. I'll try to adjust the flow sheet a little bit. Let's just see, sir. Let's do okay, remove this thing to color ratio. I think this one also like is like this. You can see, except this one that is moving away from the you understand, this one that is moving away from the pattern. Just this point here. Just this case study here. It's not like the same thing, isn't it? We have the CGS second order. You understand second order concave. Is it concave that you call this one convex? We have this one LHV. These are LHV here. Following just weeks also following the same pattern. So that's it. So we now check the last thing, which is the here to feed gas ratio. So like following the same pattern so that we can finish this thing up. So we pay this back and we change we alter this one to check the value. So it's from 1 to 2.5. Can see it here from 1 1.1 then 2.5 here. So I'm going to check it here just to get some idea how to calculate it indirectly, how to calculate your sensitivity analysis indirectly with Aspen Plus. So the result is actually easy to calculate because you have the same thing, you know, 1:1 is to give you the same flow rate of it. I mean that's the feed rate, this is the feed rate, you understand? So it's really give you the same flow rate of it. So right now we have 1 point, let me write it down, 1.508.64. So now we do the second one. We do the second one. We have 2.5, 2.5. So I will change the one to the second one. So checking the results, we have 3,771.6. So let me write that one down. That'll be second range. Okay. Now going back to default so that you don't forget things. You don't forget it when you want to, assuming I didn't put the remaining parameter back to their default. When I'm doing it now, I have to change it back to default. It's going to apply the calculation. So 1.12, 1.12. So We have that. Okay. So now we are going to make this one inactive because we don't want to be disturbing it and the sensitive analysis also disturbing it. Even the sensitive analysis is calculating. So I only deactivate one. So I only deactivate one. So we have this one also string variable, but this one is going to be conversion here now. Okay. So I'm going to change the name, the value to 1508. So that's what we forgot to do before that led to error. So 1508 and the upper range you are going to write the upper range 3771.6. So the fraction is 20, isn't it? So we change the tabulates. This one to change it to is already here to fair ratio. This is calculation mass of air divided by mass of feed, sorry. So I'm changing this to air to fair ratio. So changing it to air to fair ratio. I think that's in the same name, so I'm not making mistake. That's the same name. You have to be sure of the name. So you copy the bearing variable again, so you don't have to do it again. So you delete this and paste the one you copied. So just automatic. Write the whole thing there. So this one will also have the value 8 air to fair ratio, mass of air divided by mass of feed, and it's declared here. It's the Fortran variable. You understand? It's not like calculating it for you, and you're going to now use it as the for your plots. You understand? It's just I only did it just to have it in the plot. You understand? So that's what your client wants or what your professor wants. You understand? So we have this. So now we can purge and run this one. Okay. Just so now running. Okay, result is available. So we can check our results now. So let's check the first one. Okay, it's a fair ratio. Unless you are just going to have outline or something. So I think with this one is also having like constant value. Let's see clearly. So before we try to make any assumption, it's straight line. So that's why they didn't plot it in the thesis here. It's just a straight line. So that's what they said in the journal to use. Just a straight line. It doesn't have the effect that the air to if you add more hair doesn't affect the composition of the product. So so let me do the second plot, which is the one they plot, the one that you can see in the journal. So you remove this, so you add it here. So you can have this, which is kind of look like this. It's just because their own range for low eating value is quite bigger. So that's the end in this simulation. Well, I want to show you something when let me save this. So there is another model that I try to adjust, and that one is not giving me an error when I try to do the steam to boiler ratio. But the adjustment is just from my own logic, adding up to what they have done because they did something that fully in I am not fully in agreement with. They did something that they didn't agree with. So it's all this heat, that is because in this process there will be heat of the heat of reaction here, heat of combustion is add up. But what about this heat of gasification process? If you check it, it's having its own heat. You check the results, you are seeing this is the heat. All this heat are wasting the process and I have to just continue add it up to other process. So we have the reaction here to heat is wasting all this heat wasting from the process. So I had to add it up. So I made a new simulation which I'm going to show you now. So let me show you the new simulation. Okay, this is the new simulation. So, like I said, just the notification of the first one by adding up the heat, like making it heat. So, I think this one is more flexible that you don't need to be changing adjusting the composition. You can specify a constant heat. You understand of the composition here, like what I did there, I had to adjust the constant heat. For the heat I'm now using for the is what I got from the previous one, so that to be consistent. You understand? So what I got for the heat I put it here. You understand? So we have okay 0.591362 then 4572690. You understand? You know the total has to be 0.5119. You understand that, which is the ultimate analysis of the biomass. You understand? From the ultimate analysis from of the biomass. So we have the heat here. You understand, from the gases to going back to the gasification again. This one too is using heat up because basically everything is happening inside this system. There is no heater. This is just implicit modeling. You understand, like we're trying to do something that using adding up, mixing all the standard Aspen Plus models in order to predict the behavior of a wave. You understand? Cyclone. You understand? And gasifier. You understand? And it's working fine. You understand? It's working fine. We have this net gas coming here. You can see. So I think it's a more realistic, you understand, more accurate model if you are able to integrate the heat, you understand, out of the heat process. So that's why I did it. So and here now you can now specify the gasification temperature one in this stream here, in this place, and it will calculate the whole thing. And we have a calculator like previous ones that will calculate the temperature here, you understand, the temperature here. Yes, so so right now I'm going to finish up with the sensitivity for this one, doing for the steam, and let's see. So we have, so when we do for the stream, we use stream flow, stream variable, then mix on stream, substream mix, so mass flow. So yeah, we started from, let me check what we are quoted. Okay, 75.432 to 2715.55. So number of points you change it back to 20. You can do increment if you want, just like flexible, like. So now we just add the variable into, oh, sorry, into Balmer ratio. Now I just copy the variable here, quite handy. We have this onto into Balmer ratio, okay, and take it for, okay. You can see this one work fine without fail. So we can now check it, okay, like the first one too, but let less problem and error. So merge it to the same plot. Let's do something. Okay, something. This is not the plot I'm expecting. Let me check. So we have so check the design spec. Okay, it's not useful. This one too is not useful. Calculator is there. Okay, I should have. I have to deactivate this. This is not what I was expecting. So it's like I told you, even if you don't have it, the system tends to get a conflict interest. You will not know that if this one is working. Even if I try and check the result and the variable, you can see it's still waiting to it. So it's solving the sensitivity analysis work. You understand? So because we are altering the variable here, the calculator is also manipulating the variable. You can see the same rate is export. It's two variable, two manipulator is sending information to the same variable. You understand? So that's why I always deactivate the second calculator. So I'm going to run it and check my results now. Okay, so we have okay, this is what I'm expecting now. We have H2 and CO2 increasing here. We have the CO methane decreasing here, and we have the H2O also increasing here. That's what we got before. So so now I'm going to check the second one. You can see this one is not giving me an error again. Okay. So I think this one is now fine. You can see there's no log, all these error, the value that is diverging away from the pattern. You understand? So I think this one is like what they have here, although different process for like should I say more accurate process or something. So we have our steam to boiler ratio. That's it. Supposed to be around there. Okay, this plot. Somehow I think their CGS is different from my own here. Their CGS is quite different from my own here because of this. So we have this. So thank you very much. I think the video is not enough now. So thank you very much for staying through like watching this video. I hope you are able to learn something. So if you like the video, you can always encourage us by sharing it, you understand, and you understand, communicate with us, you understand. So the more we are able to relate to and add, you understand, we can do science together. Thank you.